The next important topic that we will look at is conditional probability, right. Once again examples we will consider collectively, right. So we are just going through the theory. So here let us say consider some events A and B. Both P and are bigger than 0. This is a very important requirement here, because you can have events, right, not they can be in some cases they arise which have right essentially end up having 0 probability, even though they are not really the null event. So we are going to put the condition right away up front that PA and PB, right, are obviously they are not the null event, right, or the impossible event. So their probability and therefore the probability can and it is greater than 0, their probabilities are greater than 0, right. So that, right, if you do an experiment, repeat an experiment a large number of times, you do observe both A and B, right. So the question is, supposing somebody told you, right, the event B has occurred, how does that change, right, your perception about A? Does it increase the likelihood of A, does it decrease it, and it turns out that the answer can be both ways, right. If you know that B has occurred, then the likelihood of A occurring or not occurring can be very significantly different, right. So knowing what is the likelihood of, now this likelihood is another term for probability, right. We are just using different words to in English that you will see, likeli, likelihood, right, A occurring or having occurred, right. So this again is a very important condition that arises often in, right, in practice, right. When you know that something has happened, there is less uncertainty in some sense, right, that you know that B has in fact happened. So that to that extent there is less uncertainty about the whole situation, right, and that obviously changes or it has a potential to change your view of A. For example now, right, if you look at n trials, right, now again I am going to use I believe yes in some previous class we used capital N for a number of trials, did we? I want to stick to that notation so that there is no confusion. We used capital N, okay. So if you consider n trials of some experiment, right, and in these n trials let us say that where A occurs NA times, B occurs NB times, and one more important thing, the joint event AB occurs NAB times, right, which can be 0 if A and B are exclusive, which is okay, there is nothing wrong in also including, right, a pair of exclusive events out here, right. So A and B occur, this is jointly, they occur jointly NAB times. So let us say you have collected this data, right. So you are not interested anymore in, let us say, the absolute probability of A, you want to only look at, right, given B means what, you are only going to focus your attention on those NB occurrences of B. So in this subsequence it turns out that NAB is the number of times that A also occurs. So NAB is clearly upper bounded by NB, this is obviously, right, there is no way that NAB can exceed NB, right. So, now you consider the ratio NAB by NB. Right, which is the ratio of the number of times you observe both A and B, as well as, I mean, divided by the number of times you observe only B, sorry, you observe B. This NB is without regard to A, right. If B occurs, then you say that you count B, right, without any reference to A. Okay. So, this ratio is exactly equal to NAB divided by N and NB the whole thing divided by NB by N, right. I am dividing by N in both. Now, if you say if N is large, right, so this ratio should be, right, reflected in the probabilistic model by the ratio of two probabilities. What two probabilities are they? Is the joint probability of AB divided by the joint, right, but divided by the individual probability of B, correct. And we know that we are dividing by a non-zero quantity. So, this ratio from the probability model, right, what does it? It aims to, right, capture this ratio, right, which is exactly equal to this. So, this is this basis for defining this ratio as what? As a conditional probability of A given that B has occurred. So, this is how our likelihood of A changes, knowing that B has occurred, right. So, earlier you may have just seen the definition, but why are we using that definition? I think, right, you should ponder about it a little bit and realize that this is nothing but this, which is very trivial to actually see, but anyhow. So, but definitely there is some intuition in writing all this. Note that we cannot put equals here, right. This is the theoretical model for this ratio, and obviously the two are never going to be exactly equal. Okay. Anyhow, this is written by definition. Sometimes this right, we are not so strict about putting the quantity being defined, right, on the right hand side, left hand side, and then its definition on the right. So, basically I am saying that this is being defined by this, right, defined as this ratio. What is this? This is the conditional probability of A given B. Please read this as one, right, one sentence. Now, some right, a word on the way in which I have written. These conditional probabilities are always written with a vertical bar. Please do not use, right, any slanted bars, right, in writing the conditional probability. Every conditioning that we encounter in this course, right, and in practice later on should always be written using only a vertical bar. And A and B should come on the same line when you typeset, right. This, if you ever have to, I am sure you will have, if you write reports you will have to do some typesetting, right. So, you do not have to worry about putting A above and B below or any such thing, right. Just put it all on the same straight line, horizontal line, right. And there is no problem, I hope, with getting a vertical bar, right. It is available in all, it is a basic keystroke, right. So, please remember to use that vertical bar, right. Do not, again, the last time let me say, write right, this is a mistake or not, I would not say it is a mistake, it is, I find this formatting so prevalent in usage that I want to say something right now, right. You do not write this, right, out in especially if you, abroad, if you go and you do not write it as A and then put some sliding bar and put B below or something, or even make it right into a horizontal bar, A divided by B kind of thing, which is meaningless, right. Some people go as far as that. So it should never be written like that, right. So I just wanted to say that very clearly. The first occurrence of this, right, has to be stressed, that it's very easily written as just with the vertical bar. Okay, so so this ratio is defined this, and then now we find that this PAB by PB, the ratio obeys all the rules that we expect of other probability measures, right. So PAB by PB are right, P, or let me call it just P of A given B, or I should say P of dot given B. So it obeys all axioms. When I say P of A given B, I am talking of any P of any event given B. You have obviously, right, not just one conditional probability, you have many conditional probabilities depending on how many events that you are looking at, right. And as we said, you have a large omega and you take f to be the power set of omega, then there is quite a lot of I mean you can do a conditioning on pretty much any event here with, right, with putting B as the conditioning event, right. So you can define a whole collection of conditional probabilities, right. Okay, so what do I mean by this? So clearly this ratio is between 0 and 1, right, can never be less than 0, can never be more than 1. When is it equal to 1? When A is in fact equal to B, right. When A is equal to B, it becomes equal to 1. When A is bigger than B, what happens? Does it exceed 1? No, it will never exceed 1, because AB can never exceed B, even if A is bigger than B. For example, if you take A to be omega itself, omega may be bigger than B, but omega intersection B is B only, right. So this ratio never exceeds B, sorry, never exceeds 1, right. So it is between 0 and 1, and then the additivity axiom is also automatically obeyed, because if A1 and A2 are mutually exclusive, A1B and A2B are also mutually exclusive, right. Okay, let me use A1 and A2 rather than A and C, right. So A1 union A2 given B, if somebody, right, wants to look at this is basically P of, I mean what I am going to write here, the first step is for any A1 and A2, not necessarily just mutually exclusive A1 and A2, you have P of A1 union A2 intersection B divided by PB. By definition, right, so this is true, this part is true for any A1 and A2, right, not just mutually exclusive. Okay, so this of course can be now simplified, right. This is just again this now we take the B inside, so this B A1 union B A2 divided by PB, right. Up to here it's right, there is no change whether, now you bring in the fact that let us say if A1 and A2 are exclusive, right, this joint are exclusive, then what happens, BA1 BA2 are exclusive, so what happens here, this becomes the sum of PB, right. So finally what will you get in the end, you will get P of A1 given B plus, do you not get this, you get it, right. So you can extend this very easily to any countable collection of events which are pairwise mutually exclusive. So therefore P of A given B obeys all the probability axioms. So in fact you get a new collection of probabilities now, all conditioned on B, isn't it? So I will just write here etc., and you can fill in the blanks, right, if you choose to, that is, right, and right, write it out for arbitrary collection of mutually exclusive pairs of events, right. Okay, so one other point here is, supposing A intersection B or AB is phi, that is A and B themselves are mutually exclusive, then what happens? This conditional probability will be 0. Let me write it this way: AB equal to phi implies that P of A given B is 0. This again makes sense, because if A and B are exclusive, if you know that B is occurred, then obviously A cannot occur, right. So this is one, there are two ends of this, right. When is it 0, when is it 1? A given B is 1 means what? A is at least as big as B, I mean in the sense of inclusion, as I said, right. The other end 0 means, and we are saying that PA is greater than 0. So if PA is greater than 0, A cannot be phi itself, but AB can be phi. So that is when this becomes 0. So there is no problem in defining P of A given B for any A in the set of sets, in the collection of sets that we have in the sigma algebra, right, or sigma field, right. So we have we really do have a completely consistent set of probabilities now, all conditioned on B, okay. Alright, so I am sure this is not the first time, this is I am just going over this fairly quickly, because right, I want to lay the groundwork again, right, without spending too much time on discussing this, but this is a very important, right, as you all know, right, conditional probability is one of the major additions to the basic theory, right, and has tremendous practical significance. So I cannot underestimate the importance of this, but I do not want to spend more time than this, because I am sure you have seen examples of this already in use, right, in your earlier exposure to the subject. So we will keep going unless there is a question. Is there a question? Okay, nobody is raising their hand. So okay, one more, I mean obviously before I move on, let me also say one other thing. There is no reason why I should only condition on B. I can create another universe by conditioning on A, for example, right. So what happens if I condition on A? Let me start that here and leave this, right. Now I am going to say, well, remove the sentence here, actually all this can be removed, right. So similarly, P of B given A is clearly PAB divided by PA, and here we have no difficulty whatsoever in dividing by PA, because we have assumed that PA is bigger than 0. Note that the numerator here is identical, this is the same PAB which occurs in both places, right. So given that numerator PAB, whether you get B given A or A given B, it all depends on what you are dividing by, that is all, right. And both cases, right, both the right, this as well as this, both of them are exactly the same in the mathematical sense. They are both conditional probabilities, and they have to obey, follow similar rules, right. What is interesting is the linkage between this and this, right. That is one form of Bayes' theorem that I am sure all of you have seen earlier, right. The fact that you have the same numerator, right. So which implies that this joint event PAB can be written in two different ways. You can write this as PAB times PB. You can also write this as P B given A times PA, right. Both of these will be important again in our later study, right. I mean this kind of construction of the joint event. So this is an easy way of thinking about this joint probability, especially in a two-stage experiment, right, which we will be coming to later on, right, where B might be the first stage and A might be the second stage, right, or vice versa, whatever, and it also sets the stage for what we call posterior probability calculation, right, where you know the output of the second stage, but you do not know what has happened in the first stage, right. The first stage is hidden, but you can observe the second stage, right. So for all of these things, this formulation is going to become very important, right? And clearly we have the base rule, which let me just say, for example, if you want to write A given B, or let me put it as B given A here. So B given A, if you want to write this, is clearly P of A given B multiplied by PB divided by PA. Right? Okay. Now it's